Hello, geometry students. Today we're going to be going over the Unit 4 workbook. So we're going to go over the entire workbook here for the Unit 4. And so let's go ahead and get started. Let me share my screen here. Okay. So let's go ahead. And mostly this whole unit is going to be about triangles. So we're going to cover lots of things about triangles, how to categorize them, all kinds of things. But one of the things we want to really, I want to draw your attention to is the Pythagorean theorem. Okay, this will be a key concept, not just in this unit, but in many things to come. Is just this idea that in a right triangle, now it needs to be a right triangle, meaning that it has a right angle, right? It has a right angle in it. So every right triangle has a right angle in it, meaning a 90-degree angle. So it'll be like an angle like this. Okay. And it has to have that sort of angle in order to be a right triangle. But if it is a right triangle, then what does this theorem say? Well, it basically says that if you take the two smaller sides, the two legs, as we call them in a right triangle, and you square those side lengths. So you take this side and you square it, and you take the other leg side and you square it, add those together, and that'll equal the longest side squared. In a right triangle, the longest side is called the hypotenuse. And it's always opposite from the right angle. So the right angle, you can think of, kind of points to the hypotenuse. Okay. And again, just to reiterate, the two smaller sides on a right triangle are called the legs, and the longest side is called the hypotenuse. So how does this formula work? So let's look at an example. And so let's go actually down to on page 4. And we're going to cover a couple of examples of what we can do with this formula. So number 6 here, it has a right triangle. We know it's a right triangle because it has a right angle in it. Okay. I also want to remind you, everything I write on here, you should write. Okay. And everything I say, you should keep that in mind and write that down too if you have the time. Okay. So anyway, so since this is a right triangle, I can use the Pythagorean theorem to find the missing side length. Okay, so that's basically what it's for. It's for, in right triangles, you can find a missing side length using the Pythagorean theorem. So we're going to be using that here. So it's a squared, again, plus b squared equals c squared. Now in our case, the a and the b are the two legs here. So those are the two side lengths here. So this would be 7 squared plus 24 squared equals the hypotenuse squared. So in our case, the hypotenuse is unknown. We don't know what that is. So, but we can use this theorem to help us find that. So to recall, 7 squared, that means 7 times 7. So 7 squared, that's 7 times 7. That's 49. Plus 24 squared. Is 576. Okay, again, that's 24 times 24 to get that. Equals x squared. We can add these two together, so 49 plus 576. So that gives us 625 equals x squared. Then what we're going to do is, to get rid of the squared, what you're going to do is square root both sides. So square root both sides of this equation. So that'll give us x equals, and then on your calculator, you want to do square root of 625. Okay, so that would give you 25. And that's your answer. So basically what we just found is we just found the side length of the hypotenuse. We know the length of the hypotenuse now is 25. Now, the hypotenuse should always be the longest side. So you know you're going to get a number bigger than the two legs here. And indeed, 25 is bigger than either of these. I also want to talk about the square root a little bit. So what the square root is saying is what number times itself gives you 625? Well, the answer is 25. 25 times itself gives you 625. Okay, so with that in mind, I want you to go ahead and pause the video and see if you could solve number 7 and number 8 here. Hold on, I'll be right back. No. I just forgot I had it in my head. Okay. Now, the Pythagorean theorem, it only works for right triangles. That's kind of key. Okay, so what happens if you do a squared plus b squared and the result is less than c squared? So they're not equal, but if you did the two smaller sides and you square them and it's less than the biggest side squared, then it actually makes an obtuse triangle, meaning that its largest angle is bigger than 90. So you can see this angle right here where C is, it's larger than a 90-degree angle. So that's an obtuse triangle. And you could tell it's obtuse by doing a squared plus b squared. And if that's less than c squared, then it must be obtuse. And you can see that here. They actually messed this up. This should say, oh, sorry, they did not mess this up. So you could see the c squared is bigger. So that means it's obtuse. And you could work that out, right? If you replace the a and the b with 6 and 11, c with 14, you would see that the right side is bigger, the c squared is bigger than the a squared plus the b squared. Okay. And again, the c is always the largest side. Okay. The c is always the largest side. And a and b, doesn't matter which one's which one's a, which one's b, but it's important that the c is the longest side when setting this up. And in this one, if a squared plus b squared is greater than c squared, then it's an acute triangle, meaning all of the angles are less than 90. So if we have a triangle like this, and we don't know if it's a right triangle, or if it's acute, or if it's obtuse, we could go ahead and plug into here. Now, if it ends up that a squared plus b squared is greater than c squared, it's acute. But if a squared plus b squared is less than c squared, then it'll be obtuse. And if it ends up being equal, then it's a right triangle. So let's see, is this acute, obtuse, or a right triangle? It shouldn't say equals here. It should be like, oh, we don't know if this is equals. There's a question mark, right? Is it equals? We don't know. Let's find out. So first, 20 squared, well, that's 400. Plus 19 squared, so that's 19 times itself, 361. And then on this side, we have 28 squared. So that's 784. Okay. We don't know if it's equal or not, so I'm going to put a question mark here. 400 plus 361, that's 761. Okay, well, that's less than this one, 784. So since the c squared side is bigger, then we would say it's obtuse. So this is an obtuse triangle. Obtuse triangle. With that in mind, see if you can do number 9 and number 10 here. So they want to see, is this an acute triangle, obtuse triangle, or a right triangle? Now keep in mind, the C is always the longest side. So when you set this up, if it has 8, 24, and 25, the 25 must be the C squared, okay? And so that'll be 8 squared plus 24 squared And I want you to figure out, is it equal? Or is this side greater, meaning it'll be an acute triangle? Or will this side be greater, meaning it's an obtuse triangle? If it's equal, then it's a right triangle. So try that one and try this one as well. Back up to page 4, they want you to do this matching here. So this should have an equals here. So for a squared plus b squared equals c squared, this would be a right triangle. If it's equal, that's a right triangle. If the a squared plus b squared is greater, then that's an acute triangle. If the a squared plus b squared is less than the c squared, so the c squared is bigger, then that's an obtuse triangle. Here, if a triangle is a right triangle, then the sum of the squares of the two legs will equal the square of the hypotenuse. That's just a fancy way of saying the Pythagorean theorem. And the converse of the Pythagorean theorem is also true, that the sum of the squares of two legs equals the square of the hypotenuse. Then the triangle is a right triangle. So make sure you got all those connections there. This concept bite, pages 6 and 7 and 8, I covered in another video, so you'd be able to find that on the Google Classroom as well. So for this activity that's on pages 6, 7, and 8, you can go ahead and watch that other video, or wait till the end of this video and watch that one. Now, on top of the Pythagorean theorem, there's also special right triangles. So there's two special right triangles that you need to know. So one is called a 45, 45, 90. So in this special right triangle, it has two 45-degree angles and then one 90-degree angle. Okay. And what I want you to do is I want you to think of these, instead of X's, I like to just make these ones. So this is like a 1. This is just a 1. And instead of x square root of 2, just call it just square root of 2. That's fine. And what does that tell you? Basically, that in a 45, 45, 90 right triangle, the two legs have the same length always. So if this length is 1, then the other leg will also be 1. So the two legs always have the same length in a 45, 45, 90. Also, the hypotenuse is whatever the leg's length is times the square root of 2. So the hypotenuse length is whatever the leg length is times the square root of 2. So if this, for example, were this length were 20, then this length would also be 20. And this length would be 20 times the square root of 2. Now, how do we use this property about this special right triangle? Well, I'll show you. So let's look at this 45, 45, 90 triangle. We know it's a 45, 45, 90 because these two angles are the same. And you can see that these two sides are the same. The two legs have the same length. So that tells me right away this is a 45, 45, 90. So what is the length of C? Well, the way I like to do it is as a proportion. So 4 is this length here, right? And I'm going to say over C. So I'm using something I know and then the thing I'm trying to find and making a fraction. Now I'm going to set it up as a proportion, but I'm going to use the triangle right here in the example. So the 4 here was one of the legs. What's the length on the leg here? Well, that's a 1. So the 4 corresponds with 1. So again, the 4 and the C come from this triangle, this 45, 45, 90. And then the 1 and the square root of 2 come from here. So notice the 4 is the leg and the C is the hypotenuse. Here, the 1 is from here, the 1 is the leg and the square root of 2 is the hypotenuse. So I'm setting up this proportion, making sure these both come from the same triangle, these both come from the same triangle, and these correspond. So leg, leg, hypotenuse, hypotenuse. I know this might seem like a complicated way to do it, but it'll make a lot more sense when we talk about other types of special triangles. So From here, with this proportion, what you would do is cross multiply. So you want to multiply the square root of 2 times 4, and then we'll multiply the c times the 1. Okay, so 4 times square root of 2, that's 4 square root of 2. And then c times 1 is just c. So what is the length of c? Well, it's 4 times the square root of 2. So let's answer questions 1 and 2 here. It says in a 45, 45, 90 triangle, the hypotenuse is how many times longer than the leg? It's square root of 2 times longer. In a 45, 45, 90 triangle, the legs are congruent to each other. Congruent to each other. Or you could write congruent. Congruent meaning they have the same length. So let's go ahead and do this other example here. So again, that's a 45, 45, 90. So I could set up 14 over c. So this is the leg length over the hypotenuse length. Now, remembering my model up here, this one, the length of the leg was 1 with the model one, and the hypotenuse is square root of 2. Now let's cross multiply. C times 1 is c, and then 14 times square root of 2 is 14 square root of 2. And there you go. This next one's a little bit trickier because in this next one, well, actually, no, this one's not trickier. Let's go. I want you to go ahead and try this one on your own, actually. Okay. Try to follow the example we did up here. Here you have a leg and you're missing the hypotenuse. So see if you can figure that out. Now, number 6 and 7, here's where they get a little bit trickier. Okay. It's not too bad, but I'll show you how to do it. So here, I would again set up the fraction. We can say 8 over a. But in this one's case, the leg is missing, right? I don't know what this leg's length is. I know what the hypotenuse length is. It's 8. And we know it's a 45, 45, 90. So we can use that same model from that other page. So the 8 is the hypotenuse, though. You see that? The 8 is the hypotenuse, and the side that's the hypotenuse from here is square root of 2, right? So the 8 from here corresponds with square root of 2. And the a is the leg, so that corresponds with 1. So now what we do is cross multiply. 8 times 1 is 8. And then a times the square root of 2 is a square root of 2. Now my goal would be to get a by itself. So what we're going to do is divide by square root of 2 on both sides. So we got a on the left side equals 8 over the square root of 2. Now, generally speaking, we don't like square roots in the denominator. So when you see a square root in the denominator, we're going to multiply by that square root on top and on bottom. So when you see a square root in the denominator, we need to do this rationalization. I know it's a pain, but the answers on the test will make it so you have to do this. So when you multiply the fractions, 8 times square root of 2 is 8 square root of 2. And on the bottom, square root of 2 times square root of 2 is just 2. Now I could simplify this fraction because 8 over 2 does simplify. So this would be 4 square root of 2 because 8 divided by 2 is 4. So now we've got it all by itself. So now we know that this length of the leg is 4 square root of 2. This would also be the length of the other leg because the legs are congruent to each other. But that would be that right there. I know that was a little bit tricky, so we'll do this one together as well. So let's set up our first fraction. So the 14 in the a from this triangle. Now the 14 is the hypotenuse. So when we think about the hypotenuse for a 45, 45, 90, that is square root of 2 for the hypotenuse, and then 1 for the leg. So hypotenuse over leg, hypotenuse over leg. So make sure it's the same type. Hypotenuse over leg, hypotenuse over leg. Cross multiply. So this would be a times square root of 2. So that's a square root of 2 equals 14 times 1, which is 14. Next, divide both sides by square root of 2 to get a by itself. Now, since we have a square root in the denominator, we don't like that. So we're going to go and rationalize that by multiplying by square root of 2 on top and on bottom. So whatever square root is here, you're going to multiply by that same square root on top and on bottom. So on top now, we have 14 square root of 2. And on bottom, square root of 2 times square root of 2 is just 2. This simplifies. 14 over 2 gives you 7 square root of 2. So that's the length of this leg, is 7 square root of 2. Okay. Hopefully that wasn't too bad. But now we're going to talk about the other special right triangle, which is the 30, 60, 90. So go back up to page 9, and we're going to look at the second special right triangle, the 30, 60, 90 triangle. So for a 30, 60, 90 triangle, that means that its three angles are 30-degree angle, 60-degree angle, and a 90-degree angle. Now, again, I want you to just imagine these are ones. So see where it says 2x, just make that just a 2. Where it says x times square root of 3, just the square root of 3 is fine. And where it just says x, just make that a 1. So what you want to remember is 1, 2, square root of 3. 1, 2, square root of 3. And in this case, the hypotenuse, the longest side, is the 2. The longest side is 2. 2 is actually longer than square root of 3. You could check with your calculator. Square root of 3 is like 1 point something. But anyway, the hypotenuse, the longest side, is 2. So it's double whatever this is. So the shortest leg, which is opposite from the 30, that is a 1. Let's think of it that way. And the one opposite from the 90 is 2. It's double that. So if this length, let's say this were length 20, then this one would be length 40. It'd be double. And then this length would be 20 times the square root of 3. Now, the one thing I want you to look at here is what's opposite from what. Now, this idea of opposites in triangles will come into play a lot in this unit. So it'll come up to play later in this video. So when you look at the 30 degree, for example, what's opposite from that is the 1. Okay, so 30 is opposite from the 1. You can go ahead and make that connection there. So the 30-degree angle is opposite from the 1. The 60-degree angle is opposite from the square root of 3. So these are opposites, the 60 and the square root of 3. And then lastly, the 90 is opposite from the 2. Okay. Now it's important that you understand this idea of what's opposite from what. So the opposite from an angle is the side that's farthest away. So the opposite from this 30-degree angle is the 1. That's the side that's farthest away from it. So these are opposites from each other. The opposite from the 1 is the 30-degree angle. The opposite from the 30-degree angle is the 1. The opposite from the 90-degree angle is the 2. And the opposite from the 60-degree angle is square root of 3. This will be a big part of this unit, okay? Now, I know that's kind of tricky, but let's go over some examples and maybe it'll start to make sense. It says, let's go to question 3 on page 10. In a 30, 60, 90 triangle, the longer leg is how many times longer than the shorter leg? It's square root of 3 times longer. Now let's go down to question 8 on page 13. It says, find the length of the hypotenuse, the C, in this 30, 60, 90 triangle. So it's a 30, 60, 90. So I would, again, like we did before, is set up first a fraction. So let's say I do C over 9. So it has to be these two things that we know or that we're looking for from this triangle. Now, what I want you to think about is what's opposite from what. So for where my C is, what's opposite from the C? Is it the 30, the 60, or the 90? Well, it's the 90 in this case. You see that? So that makes C is the hypotenuse in this case. What's opposite from the 9? Is it the 30 or the 60? Well, it's the 60. Now, why am I emphasizing this idea of what's opposite from what? Well, we need to know this information when we go back and write our other fraction. So first, the C is opposite from the 90, right? So when I go back, I want to look at back on page 9. What was opposite from the 90? A 2. So the C was opposite from the 90, and the 2 from the other one is opposite from the 90. So those correspond to each other. They're both opposite from the 90. They're both the hypotenuse. Now the 9 is opposite from the 60. So what's opposite from the 60 on this triangle? The square root of 3. Okay. So this is opposite from the 60. The square root of 3 was opposite from the 60. So there you go, like that. All right. Now that you have this, now you have your proportion. So from here, it's going to be similar to what we did for the 45, 45, 90, is we're going to cross multiply. So C times the square root of 3, and then 9 times the 2. So C times the square root of 3, that's C square root of 3, equals, and then 9 times 2 is 18. To get C by itself, what we would do is divide by the square root of 3, both sides. So that gives us that C is 18 over square root of 3. But again, remember, we don't like square roots in the denominator, so we're going to multiply by square root of 3 on top and on bottom. That gives us on top 18 square root of 3. And on bottom, square root of 3 times square root of 3 is just 3. The 18 over 3, 18 divided by 3, well, that's 6. And we still have square root of 3. Okay. And there you go. That's the length of the hypotenuse in this case. It's 6 square root of 3. Okay. Let's try this next one. So actually, let's do this next one. So here, our first fraction, C over 10, let's say. Now the C is opposite from the 60 in this case. So what's opposite from the 60 in our other triangle? Up here at the example on page 9. What's opposite from the 60? Square root of 3. So opposite from the 60, C. Opposite from the 60 on the other one, square root of 3. Here, the 10 is opposite from the 90. So what's opposite from 90 in the other one? A 2. So now we cross multiply. So C times 2, that's 2C, equals 10 times square root of 3 is 10 square root of 3. Now to get C by itself, we divide by 2 both sides. And we can simplify that, right? C equals 10 over 2. Well, that gives us 5 square root of 3. In this one's case, we did not have to do this rationalization because it didn't have square root of 3 in the denominator. Okay, we only have to do this business if there's a square root in the denominator. Okay, here the denominator does not have that. You don't have to worry about that. So that's it. You're done. C is that. So that's the length of C here. Let's do this last one, 30, 60, 90. Once again, So let's set up our first fraction, c over 10. Now in this one's case, c is opposite from the 60. You can see that there. C is opposite from the 60. So what's opposite from the 60 on the other triangle? Hopefully you remember, it's the square root of 3. Now the 10 is opposite from the 30. You see that? The 10 is opposite from the 30. So what's opposite from the 30 in our model one? What's opposite from the 30? Well, the 1. Okay, so in this case, this 10 is opposite from the 30, and the opposite from the 30 in the other one was 1. Now we can cross multiply. C times 1, that's just C. And then 10 times square root of 3 is 10 square root of 3. In this one's case, C is already by itself, so you're done. Okay, hopefully that makes some sense. Next, we're going to talk about some trigonometry. So now we're on section 4-3, and we're going to talk about some trigonometry. So the first one we're going to talk about, there's 3 trig functions here. So sine, cosine, and tangent. Now, if you have a scientific calculator, you should be able to see these buttons. They're like right here. Sine, cosine, and tangent. Okay, you can see on your calculator it says sin. You read that as sine, not sin. Then cos, that's for cosine, and then tan for tangent. So what do these 3 functions, what do they do? Well, these trig functions or trig ratios, what they help you do is you can use them to help you find missing side lengths of a right triangle. You could also use them to help you find missing angles on a right triangle. So how are they used and how do we work them? That's what we're going to go over. So the main thing here for sine, notice sine of an angle is the opposite leg over the hypotenuse. So that's why it was important to know like opposites. And you could see that. So in this example here from A, sine of A would be the opposite divided by the hypotenuse. So that's why they have A over C. It's the opposite from this angle divided by the hypotenuse. Now cosine is the adjacent leg divided by the hypotenuse. So if I'm looking from angle A, if I'm looking from here, which leg is adjacent to it? Adjacent means like right up against it or sharing a border. So if you're looking at this angle A, the leg that is adjacent, the adjacent leg is right here. See, A is the opposite leg. But from this angle, this is the adjacent leg over the hypotenuse. So for cosine, you use the adjacent leg divided by the hypotenuse. And then lastly, tangent. Tangent doesn't use the hypotenuse. So tangent is the opposite leg over the adjacent leg. So both legs here. But it's important that you do the opposite leg on top over the adjacent leg. So from angle A, you can see the opposite leg over the adjacent leg. So that's why it's A over B in this case. Now, the ratio depends on which angle you're looking from. So notice it says sine of angle A. That means you're looking from angle A. All right, or cosine of angle A, they're talking about you're looking from angle A. But if they said sine of angle B or cosine of angle B, you'd be looking from this angle, and that would change your ratio. All right, it'll make sense as we work this out, but make sure you write everything I write right here. So when it says, what is sine of angle D? Here's what we're going to write. We're going to write sine, and generally we write it like this. You don't read that as sin. This is sine. Sine of D. So sine of D equals, so we want to look from angle D. We're looking from angle D. And we want to do sine. So we want to do opposite leg over hypotenuse. So what's opposite leg from here? Well, that's lowercase d over the hypotenuse. The hypotenuse is always opposite from the 90. The hypotenuse is f in this case. So that would be sine of angle D is D over F. What would be cosine of angle D? So again, looking from angle D, we want cosine. So what do we write? We write COS for cosine of D equals, now we want, for cosine, we want the adjacent leg over the hypotenuse. So from angle D, since we're looking from angle D, the adjacent leg is E. And you go over the hypotenuse. So our hypotenuse is F. That doesn't change. The hypotenuse doesn't change depending on which angle you're looking from. The hypotenuse will always be F in this triangle. Next, it says, what is sine of angle E? So again, sine of E in this case. So now we're not looking from angle D, we're looking from angle E. So we're looking from angle E. What would be the opposite leg from there? Well, that would be lowercase e. See that? Lowercase e. Over the hypotenuse. So that's F. You may notice that cosine of D is the same as sine of E. That's okay. That's supposed to happen. Lastly, next one, what is tangent of angle E? So in this case, tangent of angle E equals, so again, tangent's the opposite leg over the adjacent leg. So if I'm looking from angle E, what's the opposite leg? Well, it's lowercase e over the adjacent leg. So if I'm looking from angle E, the adjacent leg, or the leg next to it, is D. And there you go. That's what tangent of E is. Opposite over adjacent for tangent. Now, a lot of people like to just memorize this. So, ka, toa, SOHCAHTOA. And if you just memorize this little phrase, SOHCAHTOA, then it teaches you all three of the trig functions. You see that? Because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this is just like a memorization trick. If you just memorize this, this tells you what all three of the trig ratios are. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So SOHCAHTOA. All right, maybe that'll help some of you, I'm sure. Okay, now we have an example here of how to use it on page 16, but we're actually going to skip that for now. What I want you to do is let's go ahead and go to page 17, and we're going to work out these problems here. All right, well, I'll do a couple with you, and then I expect you to do the rest on your own. So let's go ahead and do number one. It says cosine ratio for angle B. So what do we write? We write cosine, COS, of B. So cosine of B equals, and if we recall, cosine is adjacent leg over hypotenuse. So if I'm looking from angle B, the adjacent leg is 5 over the hypotenuse, which is 16. Okay, hope that made sense. Let's go ahead and do this one here. Number 5. It said, what is sine for angle A? So we write sine for A, so sine of angle A equals, and again, sine is the opposite leg over the hypotenuse. So if I'm looking from angle A, what's the opposite leg? Well, that's 9 over the hypotenuse. Now, it might be tricky to see which one's the hypotenuse, but the hypotenuse is always opposite from the 90. And also the hypotenuse is always the longest side. Okay, so this would be sine of A is 9 over 23. Lastly, let's do number 6 here. What is tangent for angle A? So tangent from angle A. So again, we are looking from angle A. Tangent is the opposite leg over the over the adjacent leg, opposite over adjacent. So this is from angle A, the opposite is 9. Over the adjacent leg, that's 12. If you want, you could reduce these fractions, but you don't have to. See if you could finish the other 3 of these. Now, how do we use these trig ratios to find a missing side length on a right triangle? So let's say we want to find this missing side of this right triangle. So how would we do that? Well, the first thing I would look at is I want to look at the angle they give us. So in this case, they give us angle A. You see that? They give us that angle A is 38 degrees. Now from there, I want to think about, okay, well, the 10 and the x, what are these sides? Well, the 10 you can see is the adjacent leg. See how this side right here is adjacent to this angle? It's not the opposite, it's the adjacent leg. Okay. And we also notice that x is the hypotenuse. X is the hypotenuse. It's opposite from the 90. So we have the adjacent, and we're looking for the hypotenuse. So which trig function should we use? Well, which trig function involves adjacent and hypotenuse? Well, that would be cosine. So we're going to use cosine in this case. And we put the angle in here. So it would be cosine 38 equals, and then we do adjacent over hypotenuse, because that's the trig ratio, adjacent over hypotenuse. Now in your calculator, we want to find what's cosine of 38. So what you do is press cosine 38, and that gives you the measure of that of what this gives you. So cosine 38, make sure your calculator is in degrees. So I got 0.788. And then we still have 10 over x here. Now what we want to do is solve for x. So we multiply by x on both sides of this equation. You always multiply by the denominator. So on the right side, we have 10. And on the left side, we have 0.788x. To get x by itself, we divide by 0.788. So that'll give us that x equals, and then we do 10 divided by 0.788, and you get 12.69, or roughly 12.7. Okay, so we got the same answer as they did. Let's see if we could do one of these on our own. So let's go ahead and do number 7 here. So the first thing we want to do is figure out which trig function to use. Should we use sine, cosine, or tangent? So first, let's look at the angle we have. So we have this 21-degree angle, angle A. Now the 10 here, well, the 10 is opposite. You see that? 10 is opposite from that angle. So we have the opposite. We have the opposite. That's 10. And the x is the hypotenuse. See, it's opposite from the 90. So which trig function involves opposite and hypotenuse? Well, hopefully you know that that's sine. Sine involves opposite and hypotenuse. So sine of 21 Put the angle always in the trig function. The angle goes there. So sine of 21 equals opposite over hypotenuse. In this case, that's 10 over x. Now in our calculator, we want to do sine of 10. Oh, not sine of 10. Sine of 21. And that gives us 0.358. On the right side, we have 10 over x. Now, to get x by itself, we always multiply by the denominator. So we always multiply by the bottom. Multiply this side also by x. So now we have 0.358 x equals 10. To get x by itself, we divide both sides by 0.358. So x equals 10 divided by 0.358 is 27.93. So that tells us the measure of the hypotenuse in this case. So now we know the length of the hypotenuse. Okay. See if you can figure out number 8 on your own. I'll give you a hint. You're going to be using cosine in this case. All right. See if you can figure out the rest. Now let's go on to page 19 and we'll do these two right here. So this is very similar to what we just did. In this case, we have this angle A is 18 degrees. And notice the 9 is the adjacent leg. See how that's the leg that's right next to the angle? So that shares that. The angle touches that side, right? So it's adjacent. That's the adjacent leg. So we have the adjacent leg, and we're looking for the opposite leg. So which trig function involves adjacent and opposite? Well, that's tangent. So it'll be tangent of 18. Tangent of the angle equals opposite over adjacent. So that's the x over the 9. Opposite over adjacent. Make sure you don't flip up this ratio and put the 9 on top. That would be wrong. Now in our calculator, we do tangent of 18. So that gives me 0.325. I'm rounding here to the third decimal place. All right, and please do put it in your calculator and everything and follow along. Now to get x by itself, we multiply both sides by 9. Remember, you always multiply by the denominator and then multiply this side by 9. So that'll give you x by itself over here on the right side, and on the left side, you get 2.92. And there you go. We just found the length of this leg. See if you could do number 10 on your own. I'll give you a hint. We're going to use tangent once again. Okay. In this case, I'll help you a little more. Tangent of this angle equals opposite over adjacent. So this would be 10 over x. So see if you could solve it from there. Okay. So it's going to be a little bit different than number 9. It's going to be actually more like the ones we did with sine and cosine. I hope that makes sense. Now let's go back up to all the way up to page 16. And we're going to talk about what else you can use trig functions for. So not only can you find a missing side length of a right triangle using these trig ratios, but you can also find a missing angle using these trig ratios. Now, how do we do that? Well, first of all, let's look at the angle we're trying to find. In this case, it's angle A. We don't know the measure of this angle. We want to find it. Now, let's look at the two sides they give us. First of all, they give us this 7. Is that the opposite leg, or is that the adjacent leg, or is that the hypotenuse? Well, hopefully you can recognize that that's the opposite leg. And then the 12 in this case is the hypotenuse. It's the longest side. It's opposite from the 90. It's the hypotenuse. So which trig function involves opposite and hypotenuse? Well, that's sine. So we're going to be using sine in this case because sine involves opposite and hypotenuse. Now the angle always goes in here in the trig function, but we don't know what that angle is. So we're going to put x here. We don't know what that measure is yet. But we know it's opposite over hypotenuse. So that's 7 over 12. Now I'm actually going to rewrite this, but a little bit differently. So I'm going to put sine of x, then equals, and I'm going to leave a little bit of space and then do 7 over 12 here. Okay. I suggest you do the same thing. Now, why would I do that? Well, the way that we cancel out a sine and we get x by itself is actually we use sine inverse. So that's going to be sine, and we write it like this, sine to the power of -1. So that means sine inverse. So we're doing sine inverse of sine of x. Now, of course, if we do sine inverse on the left side, you always do the same thing on the other side of the equation. So sine inverse on the right side as well. So we did sine inverse on the left, so we do sine inverse on the right. Now, what is sine inverse of sine? Sine inverse and sine, they cancel each other. That's the point. So that's why we do that, is to cancel out the trig function, you need the inverse trig function. So sine inverse and sine, they cancel each other, leaving you with just x. Now, how do we figure out this over here? Sine inverse of 7 over 12. Well, hopefully your calculator is like mine, but hopefully you can see that where it says sine, in purple above it, it says sine to the power of -1. And you can see with cosine above it in purple, cosine of it to the power of -1, cosine inverse. Tangent, tangent inverse, right? So how do I get that? Well, that means you have to press the second button. On my calculator, I press second. And then when I press sine, it gives me sine inverse. I don't know if you can see that there. So what I do is sine inverse of 7 over 12. I got 35.7 when I round to the nearest first decimal place. That means the measure of this angle is 35.7 degrees. That's the measure of this angle. It's 35.7 degrees. All right. So work with your calculator to make sure you got that exact answer. Okay. Make sure you're able to find how to do that on your calculator before you move on. Your calculator needs to be in degrees also. That's key. So let's do another example like that one. So let's go down to page 20, and we have a couple more examples like that. So in this one, we want to find this angle here, x again. So let's take a look at the two sides they give us. In this one's case, we have the 5 here. Well, the 5 is opposite from that angle. So we have the opposite, and then the 9 is the adjacent leg. So we have the opposite leg and the adjacent leg, opposite and adjacent. So which trig function involves opposite and adjacent? Hopefully you remember that that's tangent. Tangent involves opposite and adjacent. Remember, tangent's the one that does not use the hypotenuse. I'm going to leave a little bit of gap here. Opposite over adjacent, so that's 5 over 9. Hopefully you remember how to get rid of tangent. Use tangent inverse. So each trig function has its own inverse. Tangent inverse of this, and you do tangent inverse of 5/9. tangent and tangent inverse cancel. That's the point, leaving you with just x on the left. On the right, we could do tangent inverse of 5 over 9. So that's 29.1. When I round to the here it says round to the nearest degree, so actually we'll just call it 29. So the measure of this angle, angle X, or angle A as it is here, is 29 degrees. Next up, number 12. I want you to see if you can do this one on your own. Okay, so we saw two examples already of how to find this missing angle using the inverse trig functions. For this one, I'll give you a hint. We're going to be using sine and sine inverse in this case. Okay, so see if you can finish it from there. Okay, and then find this fraction that goes here, and then sine inverse both sides, figure out x. All right, now we're going to move to section 4-4. Now, there's a couple of things of vocabulary is angle of elevation and angle of depression. Now, you can probably already guess what those mean. An angle of depression is an angle of elevation is an angle going upwards. An angle of depression is an angle going downwards. So they have this example here with this island with a palm tree, and it's looking up at a hot air balloon. That would be an angle of elevation because it's going up. So for an angle of elevation, the object is above the line of sight. Now, what can we do with that sort of thing? Well, the same thing we could do with the other thing we were doing with trig. Okay, so in this example, we want to figure out how high the hot air balloon is, right? We want to figure out how high this hot air balloon is. Well, in this case, we would use tangent. So it'd be tangent of the angle. And remember, tangent's opposite over adjacent, so that's x over 9. We can go ahead and finish solving this. So tangent of 43. So on our calculator, we would do tangent of 43. So that's 0.933 equals x over 9. Then we'd multiply both sides by 9 to get x by itself. Again, you always multiply by the denominator of a fraction. So that gives you 8.39. Okay, that means this hot air balloon is 8.39 feet above the ground. Okay, that's pretty low for a hot air balloon. But anyway. Now we talked about angle of elevation. An angle of depression is just an angle going down. So from the bird's line of sight here, this angle going down to the mouse is an angle of depression. It's an angle going down. So angle of depression is the object is below the line of sight. Now you can use that doesn't really matter. I want you to just focus on the triangle. Really, don't really bother paying much attention to the pictures here. Just focus on the triangle. And we've seen problems just like this before, right? Here we got a right triangle, and we're missing a side length. Okay, give us that angle, 27 degrees. We're using sine. Sine is opposite over hypotenuse, so that's going to be 12 over x. The opposite side, the opposite leg, divided by the hypotenuse. Again, we can use our calculator. Sine of 27 is 0.454. Over here, 12 over x. To cancel out the fraction, you multiply by x. Remember, you always multiply by the denominator, whether that's x or some other number, just multiply by that denominator. You multiply by x over here, so it's x times 0.454. So I'll call it 0.454x equals 12. To get x by itself, we divide by 0.454. 12 divided by 0.494 gives me that x equals 26.4. In other words, that's the length or the distance between the bird and the mouse if you going straight there. See that? So that's the length of the hypotenuse, 26.4. Let's go on to this page here, page 23. Here, we just want to, they give you an example here. It says, in the graphic below, what is the description of angle 3? So the first thing you'd look at is what's angle 3? Well, that's right here, angle 3. So is angle 3 an angle going up or an angle going down? Well, angle 3 is going down from the statue's line of sight. So from the statue's line of sight, it's going down. So the answer here for the description is angle 3 forms an angle of depression, right, because it's going down, an angle of depression with the line of sight of the statue with the man below. So the statue is looking at the man below. That forms an angle of depression from the statue's line of sight. What would be a description for angle 4? So here we would write angle 4 forms an angle of, would this be an angle of depression going down or an angle of elevation? Well, you can see the man is looking upward, so an angle of elevation. With the line of sight of the, whose line of sight are we looking at? The man's line of sight, right? Line of sight of the man to the statue above. To the statue above. Sorry, my writing is not the best. I'm writing with a mouse. Okay. So really, you're just stating whether it's an angle of elevation or an angle of depression, and you're saying whose line of sight it is and what they're looking at. Okay. See if you can do these two right here. So this one's describing angle 2 here, and this one's describing angle 1. Okay. I'll give you a hint. For number 2 here, the angle 2 is the line of sight of the statue. And for angle 1 here, it's the line of sight from the cloud's line of sight. Okay. Now, again, we can use trig functions to use to help us find missing side lengths of a right triangle. So it's very similar to what we've been doing. Okay, so when we look at this triangle here, this right triangle, we want to find the height of the statue. So let's go ahead and read the question. It says, suppose the head of the statue is 57 feet diagonally to the head of the man. So from the top of the man's head to the top of the statue's head, it's 57 feet. The man is an angle of elevation of 26 degrees to the statue. And also he is 6 feet tall. How tall is the statue? So first let's find x. So we want to find x, which is the height from the top of the man to the top of the statue here. We want to find x here. So here we have this 26 degrees. We're going to be using trig ratios. Now, is this x, is it opposite from here? Is it adjacent, or is it the hypotenuse? Well, hopefully you can see that that's opposite. That's the opposite side. And the 57 feet, well, that's the hypotenuse. So we have the opposite, or we're looking for the opposite, and we have the hypotenuse. So what involves opposite and hypotenuse? Which trig ratio? Well, that's sine. Sine involves opposite and hypotenuse. So it'd be sine of 26. So always put the angle in here. Equals opposite over hypotenuse. So here, with our calculator, we do sine of 26. So that gives me 0.438 equals, and on the right side, we have x over 57. Now to get x by itself, to cancel out the fraction, you always multiply by the denominator. So that gives us 24.9, we'll say 99. So that tells us this length x. Now this one's a little bit tricky because notice this triangle starts from the height of the man, right? So you need to add an extra 6 feet to get the total height of the statue. So when we add an extra 6 feet, that gives us 30.99 is the height of the statue. Okay, that one's a little bit tricky. This one, see if you can answer this one on your own. Here you won't have to add the height of the man. You won't have to add an extra 6 feet or anything like that. You're just going to be using a trig function to help you find the distance from the man to the statue horizontally, okay? So I'll give you a hint. In this case, we're going to be using cosine. Now see if you can figure out the rest. Now let's do this one on page 25. It says, suppose a hot air balloon is 1,003 feet off the ground. The balloon makes an angle of depression of 57 degrees with the base of the mountain. How far away, x, is the balloon from the base of the mountain? So one of the key things I want you to realize is that if this is 57 here, then also this angle is also 57 here. So this is a 57 degree angle here. And we're going to be using this angle to help us find x. So we're going to be using this angle here, this 57. And I know that that's 57 because this is 57. Actually, the reasoning behind those both being 57 is those are alternate interior angles. If you remember from a couple of units ago, those would be alternate interior angles, which are congruent to each other. So that's how I know this is 57 here. Now, if I know this is 57, well, this 1,003 feet, is this opposite, or is this adjacent, or is this the hypotenuse? Well, hopefully you can see that that's the opposite leg, right? So, and the x in this case, if this is the 90, then this is the hypotenuse. So which trig function involves opposite and hypotenuse? Well, again, that's sine. So in this case, it's going to be sine of 57 equals opposite over hypotenuse. So that's 1003 over x. Now it's very similar to ones we've done in the past. So I'm going to do sine of 57. That gives me 0.839. equals, and on the right side, we have 1003 over x. Now to cancel out the fraction, you always multiply by the denominator. So in this case, multiply by x, both sides. So I've got 0.839x equals 1003. And that gives me that x equals 1196. 1196, rounding to the nearest whole number. So that means the hypotenuse, the length of the hypotenuse from the base of the mountain to the balloon is 1196. Okay, I hope that makes sense. After this is the review, and it's just everything we've already covered. And I'm going to cover that in another video also. So hope you're able to follow along. Hope you're able